So when we're talking about shape and geometry of a molecule, the first thing you actually have to understand and be able to do is Lewis dot diagrams and how to actually draw Lewis dot diagrams and the steps associated with drawing them, essentially. Lewis dot diagrams are different for different types of compounds or different types of elements or atoms. So when we're drawing the Lewis dot diagrams for elements, this is the easiest. You just count the number of valence electrons and you just draw that number of valence electrons around the element. So for example, if we're looking at oxygen, we know oxygen has 6 valence electrons, so all you have to do is draw 6 dots around it, and that's your Lewis dot diagram. Then you can look at monatomic ions and how to draw Lewis dot diagrams for those. So again, these are pretty easy. Count the number of valence electrons that the ion has. For example, if you're looking at magnesium 2+, we know that magnesium is a metal with 2 valence electrons. As an ion, it actually loses those 2 valence electrons and gains a positive 2 charge. So if we're drawing that as a Lewis dot diagram, since it's lost all its valence electrons, it has no valence electrons, so it has none of those dots. And then you need square brackets whenever you have a charge, and you just put that on the outside of the brackets. Then when you're looking at ionic compounds, that's just a combination of 2 different monatomic ions. So for example, if we're looking at sodium chloride, this is a combination of sodium as a metal, and we know that sodium loses all its electrons to give to chlorine, and it has a positive charge. And then chlorine gains all those valence electrons to gain a full outer shell, and it has a negative charge. Now, these 3 aren't as important. The main ones I really want to focus on are covalent compounds and polyatomic ions, because when we're talking about shape and geometry of molecules, we're mainly looking at the shape and geometry of covalent compounds or polyatomic ions. So there's a whole method to actually construct a Lewis dot diagram for covalent compounds. But what I'm going to do is I'm going to just do it in terms of an example. So let's look at drawing the Lewis dot diagram for carbon dioxide, for example. So the first step to drawing a Lewis dot diagram is you always have to count the total number of valence electrons. So for example, if we're looking at carbon dioxide, carbon has 4 valence electrons, and then oxygen has 6 valence electrons. So we're looking at a total of 16 valence electrons. Now, once you actually get to drawing your Lewis dot diagram, first thing you have to do is you have to assign a center atom. So in this case, since we have 1 carbon and 2 oxygens, obviously carbon is going to be our center atom. Then what you're going to do is, the first thing you're going to do is just you're going to assume 1 single bond. So remember that 1 bond here means 2 shared electrons. And then from there, you're just going to fill everything out so it has a full outer shell. So in other words, if we look at this oxygen, this has 2 electrons from the single bond, so it needs 6 more. This carbon has 2 single bonds, so it has 4 shared electrons, so it needs 4 more. And then this oxygen also needs 6 more. And then what you're going to do is you're going to count those electrons, 20. And then if it doesn't align with what you calculated at the beginning, then your electron dot diagram is wrong. And the next step you're going to do is this time assume a double bond. So a double bond means there's 4 shared electrons, and then once you do that, again, you fill everything out. So this oxygen has 2 double bonds, so it's 4 shared electrons, so I need 4 more. This carbon has 4 double bonds, so it has a total of 8 electrons, so its outer shell is full. This oxygen has 2, so I need another 4 valence electrons. And then you count. So it's 2, 4, 6, 8, 10, 12, 14, 16. And then in this case, it aligns with your total calculated valence electrons. So again, that is your correct Lewis dot diagram. So those are your steps. All you have to do is count the total number of valence electrons. Then you assign a central atom and draw everything else around it. Then you assume a single bond and fill everything else out and then check it. If it's not correct, you assume a double bond and fill everything else out and then check it. If it's not right, you assume it's triple bond. If a triple bond is still not correct, then what you're going to do is you'll assume different combinations. So for example, a double bond and a single bond, or a triple bond and a double bond, and so on. So when we're talking about polyatomic ions, it's exactly the same. The only difference is that you have to account for the charge when you're talking about your total valence electrons. So what that means is that, for example, if we're looking at this polyatomic ion, which is hydronium, this is a very important polyatomic ion in year 12. So remember that this is called hydronium. When we're calculating total valence electrons in this case, here we have 3 hydrogens, which is 3 times 1, plus oxygen, which is 6. But in this case, it has a charge of +1, so that means it's actually lost a valence electron to gain that charge. So you have to subtract 1 in this case, which is 8 valence electrons. So that's the first thing that's a bit different when you're looking at polyatomic ions. The other thing that's different is that when you actually construct your Lewis dot diagram, so in this case, so this is your correct Lewis dot diagram. Just be aware that hydrogen, the valence shell only fits. So for hydrogen, just be aware that a hydrogen atom only has a valence shell that fits 2 electrons. So a single bond is all a hydrogen really needs, because a single bond is 2 electrons. So if hydrogen has a single bond, it already has a full outer shell. So once you draw your dot diagram for polyatomic ions, the last thing you have to be aware of is that polyatomic ions have a charge. And I told you whenever you have a charge for Lewis dot diagrams, you need to have a square bracket and then draw the charge on the outside. So when we're talking about Lewis dot diagrams for polyatomic ions, it's exactly the same as covalent compounds. The only difference is your calculation of the valence electrons, as well as this part in drawing it as well, your charge on your final diagram. So when we're talking about geometry and shape, being able to actually draw Lewis dot diagrams is really, really important, because the way we actually derive the shape and geometry of a molecule is from its Lewis dot diagram. So first things first, the theory that we're talking about when we're talking about shape and geometry is Vesper theory. The Vesper theory is used to actually predict the shape and geometry of a molecule. So we're going to look at geometry first, and then we'll look at shape. So when we're talking about geometry, we're looking at the arrangement of the electron pairs, and this includes both covalent bonds and lone pairs. So what this means is that if we're talking about something like carbon dioxide, which I'll draw here, there are 2 types of electrons in this case. There is what we call covalent bonds or bonded electrons, which are these bonds here. So anything in a single or a double bond or a triple bond are bonded electrons or covalently bonded electrons. Whereas anything which is by itself, for example, these 2 electrons here, are what we call lone pair electrons. When we're talking about geometry, we're talking about the arrangement of all electron pairs. So both these bonded electrons as well as the lone pair electrons. Now this is different, as you'll see later, from shape. When we're talking about shape, all we're looking at is the arrangement of bonded pairs, and we ignore lone pair electrons. So that's the first thing you want to keep in mind when we're distinguishing between geometry and shape. So looking at geometry first, which is the arrangement of all electron pairs, to determine the geometry, all you have to do is count the total number of lone pairs and covalent bonds at the central atom. So just at the central atom. The only thing is that double bonds and triple bonds are counted as just one bond. Now that might be a bit confusing, but if it's in the same place, then that doesn't affect the geometry. Because when we're looking at geometry, for example, looking at this, we're looking at how it's actually arranged around the central atom. So if it's a double bond, it's not actually going to move this X anywhere to the left or the right. So we count double bonds and triple bonds just as one bond. So once you've counted the total number of lone pairs and covalent bonds, all you have to do is you have to look at this table and then find the geometry. So if it has one set of lone pairs and bonds, it's linear. If it has two, it's also linear. If it's three, it's what we call trigonal planar. And if it's four, it's tetrahedral. Doing an example, again, if we look at carbon dioxide, we're counting the number of pairs just at the central atom, so just at carbon. So we have one, and then we have two. And then looking at this table, this is what we call a linear geometry. So that's all you have to do when it comes to geometry. You just need to count the total number of electrons, electron pairs, or covalent bonds, and use this table to figure it out. So just quickly going through shape theory, and shape, like I told you before, is a bit different from geometry. When we're talking about shape, we're looking at only at the arrangement of bonds. So we're only looking at the arrangement of single bonds or double bonds or triple bonds. Lone pairs are all ignored when we're talking about shape. Determining the shape has a bit of a different method. The first thing you have to do is determine the geometry. And then the second thing you have to do is you have to actually count the number of lone pairs. In the fact that shape ignores lone pairs, but to actually calculate it, you need to count the number of lone pairs. And then once you count the number of lone pairs, again, you use this table to figure out the shape. So for example, if you've determined that the geometry is a tetrahedral geometry, and then you count the number of lone pairs to be 2, for example, then what you have is you have what we call a bent shape. So for example, if we're looking at something like hydronium again, which looks like this, when we're looking at geometry, this has a total of 1, 2, 3, 4 pairs and covalent bonds. So we have a tetrahedral geometry. And then when we're looking at shape, we count that there's one pair of lone electrons. Looking at this table, under the tetrahedral geometry with one lone pair, this is what we call a trigonal pyramidal shape. So most of the times, shape is the thing that a question asks about. So geometry is not that important. Geometry is mainly just used to actually find shape. Shape is the one which is really important. And the reason for that we'll go into in a bit is that shape allows us to actually determine polarity of molecules and so on.